I used to wait for the other thing to stop recording, and then I don't need to wait for that before I go to the thing. And I'll show you how I go about doing this, just how I make these. Let you see how the sausage is made. Sometimes that can be pretty scary. All right, so here we go. So let's go back to from current slide. There we go. All right, so a point, a tree, lies on the principal axis. Okay, so here's the principal axis. It goes from the center of the mirror, you know, from its maximum curvature right there. Now look at this. So this light ray goes like this. Index of notice the angle of incidence equals the angle of reflection, and they all come through. And here's an image point. All right, so here's an image point that's going to be inside of this mirror. Notice this image is going to be formed on the front side of the mirror. That's kind of weird. We're not used to that. We're going to, and that means because it's actually got real lines going through it, it's a real image. Okay, so light rays. So all of those light rays where they converged, that formed the focal length of those. That's the image point. So that formed light rays near and parallel to the principal axis are reflected from the concave and converge on a focal length. So light rays that are really close, that's how we get the focal length right there, is the distance between the focal point and the mirror. Okay, and it's also equal to 1/2 the radius of curvature. The curvature of the mirror is C. All right. There they give the geometric explanation of why it works. Again, angle of incidence equals angle of reflection, and we're looking at alternate interior, yada. Okay. Rays that lie closer are called parallaxal rays. Rays that are far from the principal axis, see, they don't really converge on the focal length. Okay. The fact that a spherical mirror does not bring all parallel rays to a single point is known as a spherical aberration. That's why things sometimes in a curved mirror aren't as clear. All right. This is a curved mirror, but this is not a spherical mirror. These are parabolic mirrors, because what happens is all of these, the focal length of a parabola, everything hits this. And so what this does is, when you're out here in the high desert and it can get really, really cold in the wintertime, that oil gets sluggish. So we use the sun to warm this thing because it reflects off these mirrors and it makes the pipes flow. All right. Now, if it's a concave mirror or a convex mirror, look, the parallaxis rays are virtual. They form at a virtual point behind the mirror. So therefore, it's a negative. The focal length for convex is negative. All right, let's write this down. Let's get some of the ground rules down again. Okay, so ladybug. So concave mirror, F, focal length positive. Convex mirror, F, negative. Focal length is negative. All right? There we got the rules down. I might have yacked enough here. Okay, so let's go back to concave mirrors here. This is if we, our class, if I wasn't gone, I might have asked you to bring in a ruler and a compass or something, and we would have done ray diagrams on our own. So here's an object in front of a concave mirror. Notice it's upright, and so what we do is we draw an axis ray like this, draw it in, angle of incidence equals the angle, it comes back like this. This goes straight in, and any ray that goes initially passes through the focal length to start, and it reflects back like this. And any ray that passes through the central, that starts from this, emanates from the central, reflects back. That is a spot on, so it reflects back like this. And if we look at where all these formed, what we see if we're standing behind the mirror and we've got an object in front of it like this, we'll see that object upside down. Now, if we move the object back here and put it upside down, we'll see a real image because the real lines are coming back, and we'll see the object up. In this case, we've got the object and it's upside down, and this time the real image is formed upright and like this. Okay. So a makeup mirror, when an object is located between for a concave mirror, if the object is located here in front of the focal length, then you get a virtual image that's upright and big. So that's where that's a makeup mirror. All right. Get a virtual image that's upright and big. So once again, between the radius of curvature and the focal length, place an object, you get a real image that's upside down. If the object is behind and it's inverted, that means inverted. And if it's behind the radius of curvature, convex on a concave mirror, then you're going to get a real image that's upright or inverted from this. In this case, they're both upright, so this is not an inverted image. But if it's in front, and there it is, it's upright. So those are nice right here. There's potential right here for a question, one of my conceptual questions. All right, now let's talk about the properties of convex mirrors. And I'll do that in the next thing. So we'll go ahead and turn this off.